Welcome back, students. As you know, in the previous lecture, we had started solving a problem, particle with a potential step. Today, in this lecture, we are going to discuss its second part. Moreover, the link to the previous lecture has also been given in the description of this video. Let us begin. First, let me brief you again about the problem of one-dimensional potential step. See students, this problem corresponds to a particle which is moving freely along the positive x direction and suddenly encounters with a hike in potential. This hike in potential has been termed here as potential step. This potential step at x equal to 0 interrupts the motion of the particle, and we have to solve for its behavior after hitting this potential wall. Mathematically, this problem can be written as that potential is 0 for x less than 0 and potential becomes V naught, finite potential, for all x greater than equal to 0. Here the height of the potential can also be set to V naught as shown in the figure. See, in the previous lecture we had discussed that in this situation we arrive at two cases. First case is which have been dealt in the previous lecture, that the particle has sufficient energy that it appears to get easily transmitted into the next finite potential region. In this lecture, we are going to discuss the second case, which which corresponds to the situation where the particle doesn't possess sufficient amount of energy, that is, it has energy less than the potential step and remains in the first region only. So, to solve this situation, to solve for the motion of the particle in this case, we will make use of Schrödinger wave equation. See, in the first region where potential is 0, the particle is moving freely, and the hike in potential, the rise in potential at x equal to 0 interrupts its motion. Now we are discussing a case, we are taking a case where the energy of the particle E is less than V naught. Mean it is not, it appears that it is not capable of getting into the region B. And to solve this, we will write Schrödinger wave equation, assuming the energy of the particle less than V naught, and then solve this equation. And we will discuss our results both in classical viewpoint and quantum viewpoint. So in the previous lecture, the results were shown in this figure, that when the energy of the particle was greater than the potential step, the resulting wave associated with the particle was able to get transmitted into the next region, but it had also certain finite probability to get reflected back in the same region A. But now we will discuss this case of energy less than the potential step. It means that this energy of the particle is very much less than the hike of potential. The height of the potential here is very much high than the energy of the particles. So in the first look, in the first inspection, it clearly appears to us that the wave associated with the particle will be completely reflected back into the first region. So let us see how this happens. First, classical mechanics viewpoint, which says that a particle will behave only as a particle. So if it is moving in the direction of the potential wall and has energy very much less than this potential, it will completely reflected back into the region A. There are no chance that it will be penetrate penetrated into the region B. So when it will be approaching the x equal to 0 position, it will just experience a retarding force, and as a result the particle will get slowed down, and as the energy of the particle is very much less than the potential step, it will not penetrate into region B and will get reflected back. Momentum of the particle can be written from the energy of the particle, and it becomes 2me under the root. And since the particle is not in the region B as suggested by the classical mechanics, so this is an impossible situation which is written here in this equation. It says that energy of the particle, if it has to be in region B, it then it must be this amount plus V naught, which is quite impossible. So we will not discuss this case in classical mechanics. So now let us see what does the quantum mechanics says for this situation. Quantum mechanics says that according to de Broglie hypothesis, every particle is associated with a wave nature. And when this wave hits the potential wall, then since the energy in the region A of the particle is very much less than this height of the potential step, it will simply reflect it back into the region A. But in order to study completely the wave behavior, we need to write and solve the Schrödinger wave equation in both regions A and B. Now you see the potential is again time independent, so we will write time independent form of Schrödinger wave equation and then solve it. This is the Schrödinger wave equation, and now we have to find its solution to see the particle behavior. So let us find its solution in both the regions. So let us first solve it in the region A. For the region A, the potential is 0. So I replace V 0 and rewrite this equation as curly square psi 1 over curly x square plus 2m over h cross square into E psi 1 is equal to 0. This equation can be further rewritten in terms of wave propagation vector k1, and how I could write it in this form. I just made use of the basic relation that we had used very frequently while dealing with any quantum mechanical problem, that P is equal to under root 2me, further P is equal to h cross k. From here, k can be written as 2me under root over h cross. And now the solution of this equation can be simply obtained in terms of exponentials like this. Psi 1 becomes the solution of this equation and can be written as a exponential iota k1x plus b exponential minus iota k1x. Now the first term represents the incident wave part in the region A, because the argument of the exponential suggests that the this wave part is moving in the positive x direction, which is the incident wave. Now in the second term, the argument suggests that this part represents the wave which is moving in the negative x direction. So this must be the reflected wave in the region A. So now let us find out the solution of the Schrödinger wave equation for the region B, where the potential is the finite potential V naught. So rewrite the Schrödinger wave equation, replace V here by V naught, and the wave function in the region B is psi 2. Now see that E minus V2, E minus V naught here is a negative quantity just because the energy E is very much less than V naught. So while writing it in terms of wave propagation vector, the negative sign appears here, which is quite contrary to the previous situation. So here again, K2 is 2m into V naught minus E under the root over h cross, since the energy here becomes V naught minus E. And again, the general solution of this equation can be written in terms of exponentials. You see, this is the sum of two terms. On observing the second term, you see that it represents the wave part in the region B. You see, if I put x as infinity in the second term, then this term will become infinite, and it should not be infinite as the wave function must be finite everywhere. So it is necessary to make this term 0 and to retain only the first term here, and this becomes the solution of the Schrödinger wave equation for the region B. Now we have got the solutions of the Schrödinger wave equation in both the regions, but still we are yet to know the values of A, B and C, the constants. So for this, I will make use of boundary condition which says that the wave function must be continuous. So the value of psi 1 and psi 2 at x equal to 0 must be equal. So I just substitute the values and put x equal to 0, and I arrive at the result a plus b equal to c. I label this equation as 3. Next, just like the wave function, its derivative must also be continuous at x equal to 0. So calculate psi 1 and psi 2, their derivatives, and their values at x equal to 0 must be equal. So these are the derivatives, and now I put x equal to 0, and now I arrive at the result a minus b equal to iota k2 over k1 into c. This becomes my equation number 4. Now using equation 3 and 4, I will try to calculate the values of a, b and c. So you see, if I add equation 3 and 4, I can get the value of c, but in terms of a. And if I subtract equation 4 from 3, I can get the value of b. That too will come out in the form of, in terms of a. So next step is to put the values of b and c back into equation 1 and 2 in order to get the complete wave function in both the regions. So these becomes the incident wave function as this, the reflected wave function b after replacing the value for b. Now side 2, which represents the probability of transmission of incident wave into the region B. So the transmitted wave function here becomes, after replacing the value for C, in this form. So now, as we now know the values of incident, reflected and transmitted wave function, we can also write the complete wave function in the region B at psi 1 and the complete wave function in the region B as psi 2. These are the complete solutions of our Schrödinger wave equation. Now you see, we need to calculate the reflection coefficient and transmission coefficient just because we need to know that how much part of the incident wave has been reflected back and how much of it has been transmitted into the next region B. So, as in the previous lecture, the reflection coefficient can be calculated as a ratio of reflected probability density current divided by the incident probability density current. The density current S reflected is calculated by the product of velocity in the region A and the probability, and upon solving and substituting the corresponding values, we arrive at this much result, which upon further solution gives unity as the value of reflection coefficient. This is a very important result, students. See, it simply implies that the reflection coefficient is 1. It means that the wave which was incident upon the potential wall from the region A has been completely reflected back into the region A just because the reflection coefficient is 1. It means that there is no chance of getting transmitted into the region B. So we can say that now in this case, the quantum results are in complete agreement with the classical predictions. But see, there is still one point to notice and explore further. What is that? It is the non-zero value of the wave function psi 2. As the reflection coefficient has come out to be 1, this psi 2 should be equal to 0 as transmission has no meaning now. Students, isn't it an interesting situation to explore? This finite value of psi 2 makes us curious to understand the wave character in the region B. So let us find out the meaning of this finite value of transmitted wave function psi 2. You might also think that are there still few chances of penetration of particle into region B? Mean, shall we think of leakage of the particle despite of its reflection, which is 100% in region A? So let us understand how this leakage is possible through the potential step. Although we have got the value of reflection coefficient as 1, it is reflected with 100% chances just because its energy was very much less than the height of the potential step. But we have arrived at a situation where the transmitted wave part is also a non-zero quantity. So at this situation, we definitely can say that the wave function does not become zero at x equal to 0. But we can also accept this situation that okay, it is decaying exponentially in the region B. It means that certainly the particle is getting penetrated into this region, but finally it will always get reflected back into the region A. So, okay, now the particle is penetrating into region B. It has some leakage into the next region. So, we should calculate what is the leakage probability of getting penetrated into the region B. So, to calculate the leakage probability, we should focus on the wave function psi 2. The probability is calculated by the product of wave function with its complex conjugate, and we are taking the wave function psi 2 since we are calculating the leakage probability of the transmitted wave function psi2. So just replace the value of psi2 here with its complex conjugate also, and you get the value of p as cc star into exponential minus 2k2 into x. You also know the value of x. So just replace it here and you will get a square into 4k1 square divided by k1 square plus k2 square. Substitute the value of cc star back into the expression for the probability, and you will get the final expression for the probability, the leakage probability, which is now a square into 4k1 square divided by k1 square plus k2 square into the exponential minus 2k2 into x. So this is the leakage probability. It means that these much amount makes the particle to penetrate into the region B, and this result is a sharp contrast to the classical predictions. Also, this negative argument of exponential simply means that this is a decaying probability, which means that with increasing x, this exponential part will make this expression a decreasing one, a decaying one. It means that it will, with the increase of x, the probability will keep on decreasing. And for this reason, we can say that the particle will always get reflected back finally into the region A. So now we should calculate the penetration distance, which means that up to which distance the particle has the probability to get penetrated into region B. So what is this penetration distance? It is the distance where the wave function psi2 gets reduced to 1 by e of its value at x equal to 0. As the wave function psi2 is quite finite at x equal to 0 and its value is c into exponential minus k2x, which on substituting the value of x as 0 just becomes the constant c. It means that it has the constant c value at position x equal to 0. And let us further assume that after crossing the distance delta x, it has reduced to 1 by e of its original value at x equal to 0. So from here, I can write an equation which means that psi2 at position delta x, it is 1 by e of the value which it has originally at x equal to 0. So psi2 at delta x, you can write it just by replacing x by delta x here, and the right hand side is 1 by e times the constant c, as the value of psi2 at x equal to 0 was just equal to c. So from here, you can easily calculate the value of delta x, which comes out to be the reciprocal of the wave propagation vector. And by replacing the value of wave propagation vector, you can get the value of delta x in terms of the parameters relating to the particle, that is h cross over under the root 2m into v naught minus e, where m is the mass of the particle, v naught is the height of the potential step, and e is again the energy of the particle. You can also notice from this expression that this penetration distance depends upon the mass and energy of the particle. It means that heavier the mass, it means heavier the particle, lesser is the penetration distance, and vice versa. A particle with a lesser mass will penetrate into larger distance in the region B. So this was all about this problem of potential step. We have discussed both the cases when the energy was greater than the height of potential step, as well as when the energy of the particle was very much lesser than the potential height. So I here give you a small exercise. You try to solve this and give your answers in the comment box. So I really hope that you enjoyed this lecture for the solution of this problem of potential step. You must be feeling excited to know about the surprising result of quantum mechanics as well. In the next lecture, we will take another interesting problem of potential barrier and will try to solve it as an application of Schrödinger equations. Thank you, students.